All right, hello everybody. My name is Jonathan Chambers. I'm a software developer at Unity, and I work on the scripting R&D team. This is scripting behind the scenes. And the plan for today is to give a two-part talk. The first part is going to be a quick overview of how scripting works and how Unity uses scripting. And then the second part is going to be an application of that to try to improve the performance of a simple little sample. And we're going to see of how we structure that and how we write our code, how it can affect the performance of our game. So in general, Unity is a native C++ application. It then hosts one of two different scripting engines on top of that to provide the user scripting experience that we do. The first one is the Windows Runtime, or WinRT, and that's for Windows Store applications or Windows Phone 8 applications. But in general, we use Mono for all the other platforms, and that's what we used for a long time. We just did the Windows Runtime recently. So what is Mono? Mono is an open source project to implement the .NET technologies that Microsoft put out a couple years ago. It's on GitHub. Unity has our fork of that on GitHub, so all the changes we make, all the bug fixes we make, all the enhancements we do to the Mono that you're running is actually out there on GitHub under the Unity Technologies group. Mono consists of a C# compiler, as well as other compilers. There's a Visual Basic one and some others, but the C# is the most popular and the most well-supported. It includes the class libraries, MS-Corelib, System, System.xml, System Core. A runtime, which I'm separating from the JIT and AOT compilers. The runtime allows Mono to abstract away the platform-specific differences of the operating systems and platforms we support. Things like creating threads, listening to sockets, accessing file I/O. And then at the end, there's both a JIT, which is a just-in-time, and an AOT, which is a ahead-of-time compiler, to compile your code into machine code that'll be run on the target. And we'll talk about that in a little bit. So the first thing that happens when you want to do scripting in Unity is you have to choose a profile. You may not choose it, we default it for you, but in general, we're always targeting one of the profiles that we support. We support a 2.0 profile, which is actually 2.0/3.5 in .NET terminology. We also have a Unity profile, which is a cut-down version of that, which removes a lot of stuff that many people don't need to give you a smaller profile, especially on mobile devices. And then we have a Unity web profile, which is a tuned version of that Unity profile, which adds security attributes so that you can't do things like read to the local file system in a web application. Your code is then compiled with one of two compilers. There's one called GMCS and one called SMCS. Historically, Mono's compiler is called MCS. That was the first version. GMCS targets the 2.0/3.5 profile, and SMCS targets our Unity and Unity web profiles. With the version of Mono we have, the compiler you run determines what profile you run against. So just by using GCMS, that's what ensures that your code and runtime will target the 2.0 platform, and SMCS will ensure you're targeting the Unity or Unity web profiles. Something many people don't know is that we do have these RSP files, these response files, and we support those. So in your project, under the assets folder, you can create a GMCS RSP file or an SMCS RSP file, and then we'll treat those as command line arguments to the Mono compiler when we compile your code. So historically, that's been the way to add custom defines. We've now exposed custom defines with a UI option in Unity, but there's still a way to add additional compiler options that we don't currently expose. In the end, this all produces an assembly. An assembly is a portable executable file, which is the standard file format on Windows for executables and dynamic libraries. It's special in the sense that it contains .NET metadata and code in one of the streams in the file instead of standard machine code. And then that assembly is also self-describing, so it has a manifest. We know what the name of the assembly is, what it references, how to locate the code, how to locate the metadata, the different classes, et cetera, that are inside. So then your game starts. We load these assemblies, and then we need to make a decision. And actually, it's been made ahead of time, which is, which sort of compilation are we going to do? Historically, in the Mono default, is to do a just-in-time compilation. What that means is lazily at runtime, the IL instructions are actually converted to an intermediate representation first in Mono, which is then optimized, and then finally that is generated into machine code, which is run on the target device. This is done per method. So what that means is the first time we would call start, for example, in your user code, that when we retrieve the start method from Mono, what we actually get is a trampoline, which is a little piece of native code that knows how to handle JITting the actual method. So we make a call on that as if it was a regular function pointer. The Mono runtime catches that in a sort of a general method. It knows who the callee was, and it knows what method I was trying to call, It then JITs that at that time, patches the calling code, so the next time we call start, it'll jump directly to the start method. There's some consideration for time versus optimization. So since this is done at runtime, there's a limited amount of things that Mono can do to optimize your code. If you do a regular C or C++ compilation in release mode, it takes a long time because a lot of optimizations are occurring. If all the optimizations Mono supported were applied, it would take a long time for your application to start up, or you would get lag times when large methods were called. So there's a good balance of optimization versus a time trade-off there. And the main constraint for a just-in-time compilation is having executable memory. So what we need to do is allocate some memory, copy over the generated machine code to that, and then mark that memory as executable, which would allow us to call that. If that memory is not executable, we're not allowed to execute that, and it'll be disallowed on the device. The other option is ahead-of-time compilation. This is the default, and actually the only thing you can do on iOS and consoles. And specifically to Unity, we do full ahead-of-time compilation. What that means is that Mono has a partial AOT option, which allows you to compile just some of the methods or some of your assemblies or some of your types ahead of time, perhaps applying a lot of optimizations to those. And then later, other things that weren't done ahead of time will be JITted. But that's not possible, again, on our target devices, so we're doing a full AOT compilation. And that full AOT compilation has a few slight overheads. So the good thing is that, again, additional optimizations can be applied because we're doing this ahead of time and not runtime. But the problem is that any type of runtime data structure that the generated code needs to access, it doesn't know where that's located. It'll locate that at runtime. So for example, if the generated code needs to access some type information, it can't locate that absolutely at compile time. And the way that's handled is through a big array inside of Mono, and everything is done through a level of indirection then. So when you're doing full AOT, there is a slight overhead to trade off against the optimizations applied, which is many types of runtime data access will have an overhead. The other thing is there's restricted features. So there's a lot of things that rely on runtime code generation. An obvious one is system reflection emit. So you won't be able to generate any new types and methods and convert those to machine code and use them at runtime. Another thing is, going back to that, one example that's commonly used, not usually in user code, but people pull in third parties, is something like a JSON serializer. So many JSON serializers, for example, would generate a serialization and deserialization method for each specific type to be as fast as possible. And on these AOT devices, it wouldn't be able to do that. Another thing is runtime generics. So generics are actually part of the metadata in the assembly. So we know about list of T, for example. It's not erased as it is in Java. So one thing you can do, for example, is at runtime, say type of list of T, and then you can use the type object to say, create me a generic instance of a list of T using int as the generic type. And then you'll get a generic instance type. That's not possible on AOT devices again. And finally, marshalling. So Mono internally, there's a number of things it needs to do to generate itself helper methods. And one thing is calling native code, for example. So when you want to call native code from your managed code, there's the manage function. That's calling a pinvoke declaration. And then you have the native C function. And what Mono does is it actually generates a little helper method in between that does some things. So it bookmarks and says, I'm about to call native code. It marshals your parameters, so your strings are being converted to char stars and any other type conversions that are occurring. It then calls that method. It marshals back the data and returns. So in these cases, all these wrapper methods need to be JITted ahead of time as well. And one of the examples people hit is, again, delegates being marshaled to native code. So if you're marshaling a delegate to native code as a callback function, it needs to generate the native wrapper function for that. And on iOS, I believe we have an attribute that you need to indicate that I'm going to use this delegate as a callback type, and I'm going to pass this to native code. Would you please generate wrapper methods for me? So let's talk about the GC. So we currently use the BOEM garbage collector, which is the default in Mono and has been the default up until very recently. So Mono outside of Unity has recently switched to SGen, but historically it's been BOEM. BOEM's a conservative mark and sweep garbage collector. And conservative, what that means is that it doesn't always know which pieces of memory that it's tracking may or may not contain references to other managed objects. So one example is the thread stacks. BOEM has to scan all the stacks of all the running threads, and it needs to interpret each location as if it might be a pointer to an object. It doesn't necessarily scan it as if it was, but it has to validate as if it could be. It's mark and sweep, which means what happens is we start at the roots, we traverse all the roots, we mark each one of the objects the roots point to, We then take each one of those objects, push them on a stack, and then we keep iterating the stack over and over until the stack becomes empty. At the end of that, any object that's not marked as garbage, it's put on a free list, and then what happens is the next time you go to allocate something, it can allocate off of that free list for objects of the same size or similar size. I mentioned the roots before when we do the algorithm of scanning. The roots in a normal application is the thread stacks, the CPU registers of all the thread states. So when you switch out, the registers are cached in there, and we can scan those. GC handles, so there's a public API to allocate GC handles for managed objects to tell the garbage collector, I want to keep this alive, even if it seems like nobody's holding on to this. Unity makes extensive use of this from native code to keep our managed objects alive. And finally, static variables in your user code are roots, and will keep any object alive that's in a static variable. One of the most important things to note is that your GC time for pause times for mark and sweep will scale with your heap size. Generally, that's only the heap that can hold managed references, and we'll talk about that in our example code. Talk about exceptions real quick. So I would say there's two types of exceptions. There's explicit and implicit. The explicit exceptions are the ones you throw. So when you say throw new not implemented exception, throw new not supported exception, any of those are actually in the IL code. If you look at the IL code in a disassembler, you'll see specific throw instructions in the creation of an exception object. Implicit exceptions are things that you don't actually have in your IL code. So null reference exceptions, stack overflow exceptions. And in these cases, what Mono actually does is it's using the underlying operating system hooks to handle these things. So one example is null references. So when Mono generates the actual machine code, one thing it could do is insert before every access to an object a check and say, if this is null, throw an exception. But there'd be a lot of performance overhead to doing something like that. And the general idea is that exceptions are some sort of a rare thing that you don't want to use control flow. So what Mono actually does is on Windows, they use structured exception handling. And on other platforms, they're using signals. And it just allows the null pointer in the generated code to be hit. That causes an access violation. The access violation is caught by Mono. Mono checks from the exception information that the operating system gives what machine code instruction actually caused that. It then has a huge hash table that can look up from native machine code instructions to managed methods, and then it can figure out where this null reference happened. So it can map from that access violation back to your managed method, and then it begins to handle the exception. So it's walking up the stack through the managed method frames looking for finally blocks or catch handlers, and then if it finds a catch handler with a filter that applies, so catch exception would catch all exceptions, it then enters that try block, pushes the exception on the stack, and then we resume normal control flow. There's a couple exceptions that are hard for us to handle, both Unity and Mono. One is a thread abort exception. The main reason for that is on Windows, there's no easy way to carefully abort a thread. So you can kill a thread, but there's no safe way, unless the thread's in an alertable wait, to abort that thread. So some people sometimes do a async operation. They'll create a thread, and it'll enter to a blocking state, or it'll do a long calculation, and they'll call thread abort to cancel that. And what will happen is, again, especially on Windows, is that may not abort. Another thing is a stack overflow exception, and the hard part there is that it may occur in native code. So you may be doing a recursive routine by accident, and it's calling into the Unity engine. And the problem there is either within Unity or within Mono, it may hit the end of the stack. Again, it'll generate a native stack overflow exception. And the problem is that Mono will handle that and then jump again to the successful catch handler. The problem is that the stack is not unwound for native code. So if there's any locks held in the Mono runtime or in the Unity engine, at some point later, you're probably going to hit a deadlock because someone's going to try to acquire that lock, and the lock is still being held on the thread that was jumped back to your catch handler. Debugging. We use the soft debugger in Unity. What that means is that Mono runtime is aware that it's being debugged. There was an old hard debugger in Mono at one point, and what that means was the operating system, or the debugger code was using operating system hooks to actually pause the Mono process and read memory and write memory direct to the process. In this case, when Mono starts up, it spins off a thread, and it uses some code called the debugger agent, and that thread basically listens on a socket, and clients can connect to that, either Mono Develop or Unity VS, for example, uses the same mechanism. And then they can get information out of the debugger. So every time every method is JITted, a new type is loaded, it sends a message over this socket, over the wire, to the client, and that client can present that in the user's UI. When you want to do debugging, there's an option in Unity to choose script debugging. The reason we give you that option is because it's slightly slower. At a sequence point, which is any place you'd possibly want to stop, we insert these sequence points, so that's like before and after a method call, after a variable assignment, before returning from a method. And there's a few empty instructions in the machine code. And what happens is whenever you want to do a breakpoint or a single step instruction, we actually change those no op instructions to read from a page of protected memory. What happens then is, again, the operating system creates a seg fault, and then we can look up and see, was this one caused by a breakpoint instruction? And then we pause all the threads in the mono process while you're looking at all the information in mono develop or Unity VS again. You can look at the call stacks, evaluate variables. And again, one of the things that causes most of the instability in the debugger is these deadlocks again. Because what happens is you hit that event, a type load or an exception happened, and so that's happening on some thread. That then requests that all the other threads pause because we want to inspect stuff in the client debugger. And the problem is that some of those other threads may be holding locks, the same as we talked about earlier. And what happens is we go back to the client, you may type in a variable, an expression you want to evaluate, that calls back into Unity and Mono, and it tries to maybe JIT a method that hasn't been JITted yet, and it won't be able to acquire the lock to do that because it's held on another thread that's suspended. So that causes most of the deadlocks that people see and report. And we are working on that and looking at that, but it is a complex problem. Okay, so native interop. Unity uses internal calls. The other option is platform invoke, and the main difference between that is what happens to the arguments. The internal calls, nothing gets marshaled, so Unity is well aware of how Mono lays out things internally, and those things are passed to us directly as they're represented internally, rather than being marshaled. Again, for a string, we get the internal Mono representation for a string, rather than being marshaled to a char star or to a WChar star. If you're using platform invoke for native plugins, the one thing you want to look out for performance reasons, is mainly marshalling. So when is marshalling going to happen? These types going to be converted. For plain old data types, they're just being blitted across, so that will be very fast. For arrays, they're being passed directly to you. They're offset to where the data lies for an integer array, for example, and passed to native code, so that's fast. The most common thing that causes issues is passing strings. So every string needs to be converted into whatever type you specify. When you do a platform invoke call, you specify via marshal attribute or take the default marshalling what that will become to your native code. Normally that's a char star. So for every string, we need to allocate a corresponding char star representation of that, copy the memory over, and pass that into native code. And if this is something you're calling a lot, that can lead to performance issues. So that was a real quick run through of how things work, and now we're going to try to apply that to something useful. So we're going to do an example. This example is just a character. The character has a string name and a 3D point, which is a position, and we want to have 100,000 of these characters, and we're going to time the performance of two things. One is, how long does it take to update all 100,000 characters' positions? And the other thing is, how long is the GC going to pause every time the GC runs? So we're measuring here the lower bound. So when I'm doing these measurements, and you'll see, we're not actually creating garbage. So the GC, as I said before, scales with heap time. It's not actually the time to collect the garbage and mark that to the free list. We're not going to create any garbage. We're just going to call collect, collect, collect. And what that's going to do is, all it's going to do is mark all the live objects, and then it'll be done. So this is now our lower bound, because as you go forward in your game and you start allocating garbage, it's never going to be faster than this, because it's always going to mark all the live objects, but additionally, it'll also have to sweep the dead objects as you go forward. So this is giving us a lower bound of GC pause times going forward. So the setup, we have a simple class called approach, and it's abstract, because we're going to have a couple different approaches that we're going to walk through of how we handle this. We have one method, setup, which is the length of the character array we want to use, which is 100,000 in all these examples. And the other thing is an update method, which takes a vector, and all we're going to do is add that vector to the current position of each character. I have this helper method, time microsecs, and what we're going to do is pass it an action, an iteration. It'll run that action iteration times and return the average time for that. In this case, we're using average time. You could also look at worst case time, but the average in this case makes sense. So the first thing we're going to do is we're going to loop over each approach, and in this approach, we're going to call update for a vector of ones 100 times. The second test is just going to call system GC collect, which does a full garbage collection, and we're going to do that 100 times. And again, average those values. And again, to summarize that, we did this on 3 different platforms. I did this on my MacBook. I did this on my Nexus 4, which is a fairly new smartphone, and I did this on an iPod 4G, which is still supported by Unity, but is about a 3 or 4-year-old single-core mobile device, and we'll see how these performed. All right, approach 1. So we have a character. This is the most naive approach here. You're going to have a character class, right, with a public field string and a public field vector3, which is a position. And to store those 100,000 characters, we're just going to have a character array called characters. Our setup takes the length, it allocates an array of that size, it loops over the array. For every index in the array, it has to create a character instance, and then it also has to set the name field of that character. In our update, it's really simple. We're just going to loop over the whole length of the array. We're going to retrieve each character, its position, and add the vector to it. So this is what our heap memory is going to look like. We're going to have a character array of one contiguous piece of memory. That character array is actually pointers to character instances. Each one of those is a piece of memory that is probably not contiguous. And then each one of those characters has a pointer to a string object, and it also has the XYZ of the vector3 contained within that character as well. So if we look at this, again, the character array is pointer size. We'll assume we're 32-bit. We have about 390 kilobytes in the character array. We have about 1,600 kilobytes in the character instances, and then we have the strings. I color these two different colors. The string is our blue, and the other ones are red. That's because the red ones need to be scanned by the garbage collector. So Mono does tell the garbage collector when it's allocating memory that may reference other pieces of memory. So when we allocate strings, strings never reference other objects. So that does not need scanned by the garbage collector. But the entire character array and each character instance needs scanned because it might reference and keep alive other objects. And what you'll see there is it actually changed. And that's because of the overhead of an object. So every object in Mono, and I believe .NET, has a overhead of 2 pointers per object. So in this case, that's 8 bytes per object. So we just went from 1,600 kilobytes to actually 2,400 kilobytes to have all these different character instances. So we're scanning at this point about 2,700 kilobytes of memory with the garbage collector. Here's the times. They're not very illustrative at this point, but what you see is there's about a 5 times factor of difference between OS X to Android on a modern smartphone, and then another 5 times difference going to iOS for our update operation. You also see a big difference in GC pause times going from OS X to the mobile devices, I'm guessing because of the memory throughput. GC is a very memory-intensive operation because it's scanning through the entire heap or whatever parts of the heap it needs to. So we're going to take a quick detour. I set up this example to show something, and it wasn't working out. So the golden rule of performance is to not assume anything. And in this case, I assumed something, and I was proven wrong. So we're going to see, in this case, something besides what I was intending to show, but something good to show anyway. So if you look at our update function, we're looping over all the characters in the array. We're retrieving the character's position and adding the vector. So what's that line actually doing? So that's using the addition operator, actually the shortcut addition operator. We can't overload that in C#. We can override the addition operator. So the compiler is actually calling the addition operator for us on a vector3, which we actually override. We do override that in Unity, so it's actually making a function call there. So that function call takes 2 vectors. Then it actually constructs a vector. This code is a little bit misleading because it's not actually newing an object onto the managed heap because vector is a struct, but it is actually initializing a vector by calling its constructor. So we have 2 function calls occurring here for our little plus equals operation. So let's take a different approach and see what happens. So let's just retrieve our vector3 from the position of the character. Let's add each of the x, y, and z individually. We're using the plus equals operator again, but in this case, x, y, and z are floats. Simple types are actually implemented via an add opcode in the IL code. So this is going to be an opcode instruction, not a method call. And then we'll copy back to our position. So again, these numbers aren't illustrative. We'll see here in the chart. So in OS X, we're over twice as fast calling update by using the inline code there rather than using the plus equals operator. So this is just an example to show this. I don't want everybody to leave here and say the speaker said we should never use the plus equals operator on vector3. The point is that the performance difference here is drastic, and we found that by looking into what was going on. If you look at the other platforms, Android's not quite twice as fast. If you notice, the GC times for OS X and Android are the same. We didn't touch anything that would affect the GC, so that makes sense. And again, iOS is faster as well. So what happened? So we really don't know. I didn't have time to actually look into the generated assembly code and see what's going on, but we do have function calls happening. Those function calls may or may not be optimized away by Mono, depending on the inlining heuristics. We also have value types. Mono, it sometimes does disable certain optimization operations if you're returning a value type, and we're returning a vector 3 from that method call. So let's keep proceeding now. We already sped up our update, and now we're going to change our character to be a struct instead of a class. So all we do is change this one line. We still construct the character array, but note now that the character array is not an array of pointers to characters anymore. It's now an array, a much larger array, to hold the characters in line in the memory allocated in that character array. So what you see is we new up the character array, but then we don't need to construct character instances because they're actually inlined to the characters array itself. All we need to do is set the field name. And the same thing here. When we're retrieving the characters, it's only doing a much closer memory lookup. It's not retrieving the character and then retrieving the field from the character. It indexes into that array, and then the position is basically right after the string field. So it's only incrementing by a pointer size to retrieve the position rather than doing another memory read from the character instance to get its field. In this case, this is what our heap looks like. We have a single character array. It's much bigger, but overall, the memory that our garbage collector needs to scan went from about 2,700 kilobytes down to 1,500 kilobytes. We saved, first of all, the 8-byte object header for every character object we're not creating now. We're also saving the indirection of a separate character array, so there's 4 bytes. So we have saved 12 bytes for every character at this point. Our memory is also contiguous, so the GC can optimize for that, and it can scan contiguous sections of memory very fast. Again, there's the times. So performance went down a little bit, but what you see is the pause time is halved on OS X. So we went from 8 milliseconds to under 4 milliseconds. Similar results on Android, and the performance differences are actually a little more drastic on the left side there. And similar on iOS to Android. Okay, and here's our final approach. And we're going to separate it into an array of strings for the names and an array of vector 3 for the positions. This is all internal to these approaches, so the clients don't actually know how the difference between how we're storing our characters. We can do that all internally, so we're free to play with this. And what we're going to do is allocate an array of names, an array of positions, and then initialize all the names here. When we do our update, all we need to do is retrieve that vector 3 from the positions array. And here's what our memory looks like now. So we have an array of strings, which is only 390 kilobytes. Again, it's 100,000 pointer size values. That points into all the string instances. And then we have a huge array, memory-wise, of vector 3s, but Mono knows that there's no possible way any of that memory can reference other objects. So the GC doesn't need to scan that. So in this case, we went from about 2,700 kilobytes down to 390 kilobytes of contiguous memory that the GC needs to scan. What we see is some more improvements on OS X for the pause times, as well as performance. Same on Android, and most on iOS. So we halved our pause time the last step, and we halved it again. So the pause time on iOS is now a quarter of what it once was when we first started. So to give the summary of that, we have a net savings of all memory of about 1 megabyte. That's all memory total. We have 7 times less GC scanned memory that could contain references to other memory. It's all contiguous, and we saw a 3 to 4 times speed up in the GC collect depending on your platform. Update performance, most of that came from discovering the vector addition operator, but we did see speed ups from the memory layout, especially on the mobile devices. So we saw around a 2 times speed up depending on your platform for the update. That's it, we're out of time. I am available at the hands-on lab. There's a scripting team out there. There's 2 of us or 3 of us. Feel free to stop by for questions, and thank you guys.